We have just seen that we can visualize the electric potential created by a positive charge as a hill, in that a change in electric potential is described as a change in height. This representation is a powerful way of thinking about the electric potential. The steepness of the hill represents the strength of the electric field. This picture reinforces the fact that absolute height is not important. What matters is the change in height, i.e., the electric field is determined from this change in height, from the steepness of the curve, which certainly does not depend on what particular height you call zero. We can choose zero to be anywhere. For a collection of point charges, we usually choose zero to be at infinity, whereas geographic heights are usually given relative to sea level. We can develop this graphical picture further by including a new quantity, an equipotential, the locus of all points having the same potential. Clearly, in our picture, an equipotential results from intersecting a plane of constant height with our potential surface. Here we see equally spaced stripes from the side view of the potential plot. As we rotate the plot so that we are looking directly down at the potential, we see that the stripes no longer appear to be equally spaced. This view gives us the two-dimensional projection of these equipotentials in the xy plane. Note that the spacing of these equipotentials, the red circles, increases as we increase r and move away from the origin, the location of the positive point charge that is creating this potential. We now superimpose the radial electric field lines produced by this positive charge. Note that these field lines are always perpendicular to the equipotentials. This is a completely general result, since to move between points in the direction of the electric field requires work to be done. The potential must change. Consequently, an equipotential must everywhere be perpendicular to the electric field. Note that we have chosen to represent the equipotentials using constant spacing in potential, just as a topographic map displays contours of constant elevation using constant spacing in height. Therefore, at places where the equipotentials are close together, the potential is changing rapidly, i.e. a strong electric field, while at places where they are far apart, the potential is relatively constant, i.e. a weak electric field. Since potential is a scalar, the potential created by a combination of charged particles is just the scalar sum of the potential created by each individual particle. Here we see the potential created by an electric dipole. Note that while the positive charge creates a hill, the negative charge creates a valley. We'll now move on to some specific example calculations of potentials.